Bismillah ar-Rahman ar-Rahim. Now let's start with the lecture number 4, which is about the analysis of statically indeterminate trusses. And this analysis will be using the flexibility method. So we will now be analyzing the statically indeterminate trusses using the flexibility method. Flexibility method, already we applied it on the beams. Also we applied it on the statically indeterminate frames, and now we will apply it on trusses. Okay, so the topics we will be discussing in this lecture are, first we will introduce this flexibility method for trusses. Then we will review some prerequisite topics. Okay, we will review the how to find the static indeterminacy for trusses, and also we will review the unit load method for trusses. Okay, then we will discuss the stepwise procedure for trusses, and then we will solve example problem number 1 and example problem number 2. Okay, so how you define a truss? Okay, a planar truss is a system of members, and those members lie in a plane and are interconnected through hinged joints. Okay, we idealize a planar truss to be a system of members which lie in a plane, for example XY plane, and all the members of this system are connected through hinged joints. And we assume that all the forces are acting in the same plane in which the system is lying. Okay, and the external couples are assumed to have their moment vectors normal to the plane. Okay, so the moment vectors of all the external couples, they will be normal to the plane in which the system is lying. Okay, so now this is a truss, this is a planar truss, a 2D truss. Okay, these are the different members of this truss structure. This is one member, this is another member, similarly these are the other members, and these members are connected through hinged joints. You can see them, they're connected. So such a system of members, we call it truss. Okay, we call it a truss. So the loads that can be applied on a truss, they can be which are applied at the joints directly, or there can be loads which act directly on the members. Okay, we can have forces on the joints, or we can have members on which the load is acting directly. For the analysis purpose, we can replace those loads which are acting directly on the members by a statically equivalent loads that act on the joints. So we obtain, by doing so, we obtain a truss structure in which the loads are only acting at the joints, and there are no loads then acting on the directly on the members, because we have replaced them by statically equivalent loads which act at the joints. So now what will be the member forces due to the loads? So the member forces, if your structure is subjected to joint loads, in this case, our member forces will consist of axial forces only, okay? And the axial forces, of course, they can be tension or they can be compression. Whereas in case where there are loads acting directly on the members, then in that case, we will have bending moments and shear forces also in the members in addition to the axial forces, okay? Now, why we are using flexibility method? So we know that the flexibility method is in the matrix form, and the advantage of this method is that the matrix form organizes the work. The matrix form, writing in matrix notation, it organizes the work, and there are then less chances of errors. So that's why we call the flexibility method a systematic method, because we present this method in the matrix form, and the matrix form has the advantage that it organizes the work, and there are also less chances of error. Now let's review the topics, the prerequisite topics. The first is to find the static indeterminacy for a given truss. So the formula for finding the total static indeterminacy, this TSI, it stands for the total static indeterminacy. It is given by B plus R minus 2N. Now, what is B? B is the number of, so this is not the frame, this is the, B is the number of truss members in this case. B is the number of truss members. R is the number of support reactions. R is the number of support reactions. And N is the number of joints. N is the number of joints. So if you plug in these values in this equation, this gives us the total static indeterminacy. And what is total static indeterminacy? It is the total number of extra unknowns which cannot be solved using the available equilibrium equation for a truss structure. Now, this total static indeterminacy is a sum of, external static indeterminacy, which can be determined by this equation, which is R minus 3, where R stands for the total number of support reactions. Okay. So it means that the external static indeterminacy, it will give us the total number of extra support reactions, which cannot be determined using the available equilibrium equations. Okay, external, it means the extra support unknowns. So the total static indeterminacy is a sum of the external static indeterminacy and internal static indeterminacy. And internal static indeterminacy deals with the extra number of member forces which cannot be solved using the equilibrium equations which are available. Okay, so it means that the sum of this external static indeterminacy and internal static indeterminacy, it is equal to the total static indeterminacy. So if we have the formula for the total static indeterminacy and the external static indeterminacy, so we can find out the formula for the internal static indeterminacy by subtracting from the total static indeterminacy this external static indeterminacy. Okay, so this equation is for the total static indeterminacy, and this equation is for the external static indeterminacy. So if we if we subtract this external static indeterminacy from this internal static indeterminacy, what we get? We get this. This is the number of truss members, B. This is R. R is the number of support reactions, minus 2n. Now this minus will multiply with this R, so this becomes minus R, which are the support reactions. And this minus into minus will become plus, so this is now plus 3. Okay? So we know that the total static indeterminacy is coming from the sum of external static indeterminacy and internal static indeterminacy. External is dealing with the unknown support reactions. Internal is dealing with the number of member forces, okay? Number of member forces. Okay, so now if we simplify this equation, we get this equation for the internal static indeterminacy, which is B plus 3 minus 2, and this comes from this equation, okay? So now if you want to find the internal static indeterminacy directly, you can find it by this equation. Now let's apply this to a truss structure. This truss structure has number of members equal to 10, okay? This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7, 8, 9, and 10. We have 10 truss members. What is N? N is the number of joints. How many joints we have? 1, 2, 3, 4, 5, and 6. This is not a joint. This is not a joint. Remember, this is not a joint. Joint is where members are connecting and they are transferring forces. Okay? So, this is not a joint for sure. So, our total number of joints are 6 in this structure. And what are the support reactions in this case? So we have 2 support reactions at this support A, and we have 2 support reactions at this support D. So total number of support reactions are now 4. Okay. So if we want to find the total static indeterminacy, we need to plug in these values into this equation. So we get B plus R minus 2n. So the total static indeterminacy in this case is equal to 2 degrees. But now, as the total static indeterminacy, it consists of both the external as well as internal static indeterminacy. External means the number of extra support unknowns, whereas the internal means the number of extra member forces, which cannot be solved using the available equilibrium equations. So from this total static indeterminacy, we now don't know that whether these 2 degrees are internal or external, or one of them is internal and the other is external. So in order to find this, we now calculate the external static indeterminacy, which comes from the equation, this one, R minus 3. R is the number of support reactions, which is 4 in this case. So 4 minus 3 gives you 1. It means that there is 1 external static indeterminacy, 1 extra support unknown. So we automatically now get to know that if 1 is the external, so 1 will be internal, okay? Why 1 will be internal? Because total minus external, so total is 2, minus external is 1, so 2 minus 1 is equal to 1, okay? So you can also find this by plugging these values into this equation, which we developed here, okay? The answer will be the same. So it means that we have 1 extra member force also, and we have one extra support reaction also, okay, which cannot be solved using the available equilibrium equation in this case. Okay, so this was about the static indeterminacy. Now we move to the unit load method. The method is the same as we did for the frames, with some changes here in this equation. If you remember, for frames, this equation was capital M. There was a capital M here, right? There was a capital M and small m, if you remember. And there was EI. Now we are using this EA. So let's study what is DRL. DRL, you know that this is the displacement. This is the displacement corresponding to any redundant location R in the truss structure. And this displacement is coming from the externally applied load. Okay, so we call this displacement as DRL value. Okay, and we can calculate this DRL by this equation. And in this equation, I is the current truss member, M is the total number of members in the truss. So you actually apply this term to each member of the truss, and then you add them. Now, how you apply them? Now let's see this. We have what we have in this term. We have P, and what is capital P? P is corresponding to the axial force, which is the member force. Axial force in what? Axial force in the member I, which is under the consideration. And from where this axial force is coming? This axial force is coming from the externally applied load. Okay, this is coming from the externally applied load. So if you apply external load on your truss structure, and then you analyze your whole truss, so you find out the member forces actually, and then the member force in each member, it will correspond to this capital P. It can be compression, it can be tension. So if there is tension, we will then put a negative sign with this, and if there is compression, we will then take it as positive. Okay, compression will be positive in the member in this equation, and tension will be negative. Okay, this is our convention here, sign convention. Okay, now what is this U? So if P is the axial force, this U is also an axial force, and this force is again in the same member which is under the consideration, member I, but the difference is in the load, and this time we don't have any externally load applied. Rather, we have applied a unit load, and that unit load is applied corresponding to the redundant location R. Okay, corresponding to redundant location R, you have applied a unit load, and then you have solved the whole truss, so that the axial force in each member, now we will be representing it by this capital U. Now what we are left with? We are left with this L, and L is nothing but it is the length of the member under the consideration. So if you are talking about the member I, this will be the length of the member I. So what you are doing actually, you are multiplying the axial force due to externally applied load, the axial force due to the unit load applied corresponding to redundant location, and you are multiplying with the length L. And this product, then you are dividing it by the EA, where E is the modulus of elasticity of the member I, and A is the cross-sectional area of the member. So it will always be given there in the problem, this value of E and this value of A. Okay, so if you solve this for one member, then you need to go to the next member and repeat the same, and then add with the previous one. So you keep on going to the next members, and you keep on adding with the previous. So by doing so, you get the DRL. Okay. Now, let's discuss this flexibility coefficient matrix also. Now, these are again the displacements, but now these displacements are not coming from the external loads. Okay, they are not coming from the external loads. Rather, they are coming from the unit load, which is applied at a redundant location. So if we are finding the displacement at J due to a unit load applied at K, so this can be found by this equation, in which again this I is the current member under the consideration, truss member. M is the total number of truss members. What is now this U? Okay, so now this U subscript Ji, this is actually the displacement at J due to unit load applied at I. So we can determine this by this equation, and in this equation this Uji will be corresponding to the axial force. This will be the axial force in the member I, and this force will be coming from when a unit load is applied corresponding to redundant location J. Okay, this is Uji. So you apply a unit load at redundant location J, and then you find out the axial force in each member. So that force will be represented by U subscript Ji. I stands for the current member number, okay? And J means that the unit load is applied at location J, redundant location J, okay? Similarly, UKI, there's only one difference in this previous. It is again the axial force, but this axial force is coming from when the unit load is applied at the redundant location K. So there can be more than one redundant locations depending on the situation. If you have more than one redundant location, so then when you apply a unit load at any redundant location, then the member forces in the members will be represented by writing in the subscript that redundant location, as we have written here, K and J, right? Because the unit load is applied at J and at K. Now, the remaining terms are exactly the same. M is the number of frame members. L is the length of the member under the consideration. E is the modulus of elasticity of the member, which is the truss member here. And A is, of course, the cross-sectional area. So by plugging these values for one member, and then in the next member, and then in the next member, until the last member is reached, and then by adding their results, we get the flexibility coefficient. Okay, we get this flexibility coefficient. So now let's move forward. We will discuss this in detail in the example problems. Okay. Now let's discuss the stepwise procedure. Stepwise procedure will be the same as we discussed for beams and frames, with some changes. Now let's see them stepwise. First, we have to find out the degree of external and internal static indeterminacy. Okay, so why you are finding external and internal? Because you want to know that how many support extra unknowns we have and how many extra member unknowns we have, so that accordingly then in step number 2 you can then choose the redundant actions. Okay, then you can choose accordingly your redundant actions by releasing the constraints. By doing so, you obtain your basic determinate structure, BDS. Now, if, for example, your truss structure is externally and internally indeterminate, as we did on the previous slides. There was one slide in which we determined the static indeterminacy. So there was 1 degree external as well as 1 degree internal static indeterminacy. If you have such case, then in the step number 2, we will then choose redundant actions for member forces as well as for the support reaction. So if there is 1 extra member unknown, we need to release that and we need to choose 1 redundant action there. And as we also have 1 extra support unknown, so we need to release that and we need to write 1 redundant action corresponding to that support reaction also. Hope this is clear. So then in the same step, you calculate this DRS matrix. And again, this DRS matrix corresponds to the support settlement, support translation, or support rotation. Okay, and all these translation, settlement, or rotation, they will be corresponding to the redundant actions which we have chosen. Okay, which we have chosen. Okay, now this BDS which we have obtained here in the step number 3, now we will be performing analysis on this BDS, this basic determinate structure, under different conditions. First, we will analyze the BDS when subjected to the external load, the given external load. And you have to compute the member forces, and those member forces will now be denoted by the capital P. By the capital P. Okay. Next, you analyze the same BDS, but this time you analyze this for a unit load. You apply a unit load corresponding to a redundant location number 1, and then you find out the member forces in each member, and these member forces are called now U1 because you applied the unit load at redundant location 1. Okay. Similarly, when you apply a unit load corresponding to redundant location number 2 and compute the member forces, it will give you the values of U2. Okay. These are the axial forces, and from where they are coming from the unit load which was applied corresponding to redundant location number 2. Okay. Now, in the next step, you need to arrange all these member forces. You need to arrange all these member forces in the form of a table so that you can, your work can be efficient and there are less chances of error. Okay, so that there are less chances of error then. So this table we will be discussing in example problems for sure. Now in the step number 5, what you do, you calculate the DRL matrix, and this DRL matrix is coming from where? It is coming from the values. It's coming from the values which are the displacements. Now, displacement values where? Displacement values corresponding to the chosen redundant locations. Okay, chosen redundant location in the BDS due to externally applied load. So we will be picking the values which we have calculated in this step 3, and we will be using them in the step 3 part A, and we'll be using them in the step 5 for computing the DRL matrix. Similarly, we will be computing the flexibility coefficient matrix. Okay, and the flexibility coefficient matrix, they can be the coefficients, they can be calculated by applying a unit load at one redundant location at a time and then solving the whole member forces. Okay, so this way you can find out the flexibility coefficients. So once you have the flexibility coefficient matrix, you have the DRS matrix, you have the DRL matrix. So you simply put them in this equation so that you find out the value of your unknown redundant actions. The next step, we solve for the member forces. And the member forces are coming from this equation, in which the AML we know from the frame analysis. In this analysis now, these are the member forces, and the member forces which are coming from where? The member forces which are coming from the external applied load. Okay. Yes. Okay. So AMR is coming from the unit load applied at one redundant location at a time. So for two redundant actions, AMR matrix will consist of two columns. The first column will be coming from when the unit load is applied corresponding to redundant location number 1, and the second column will be coming from when the unit load was applied at redundant location number 2, and this AR is coming from this equation. Okay, so this way we will find the member forces. Now let's solve this truss structure, this given truss structure. Now we are given that analyze this truss using the flexibility method. Okay, we have how many members in this truss structure? 1, we have 2, we have 3, we have 4, we have 5, and we have 6. 6 truss members. Okay, and how many joints we have? 1, 2, 3, and 4. These are the external loads acting at joint C. Okay, we don't have any member force, we only have joint forces here, and we are given that you have to take EA equals to constant. Okay, now the length of this member and this member, this is equal to 20 feet, while as the length of this member and this member AC, this is equal to 15 feet, and this is given. We can find out the length of this member for sure by using this length and this length. We will be doing it when we need this, okay, in the coming steps. Now, the step number 1 is to find out the static indeterminacy. And the static indeterminacy, in this case, let's get rid of the total static indeterminacy first. B plus R minus 2n. What is B? B is the number of truss members, which is 6 in this case. Number of support reactions R, which is 3 in this case. 2 at this support, 1 is this support at this support. Okay, so this is 6 plus 3, and n is the number of joints. So we have 4 joints here. So this is 2 into 4, 8. So we have total static indeterminacy equals to 1 degree. Now we know that we know that now that this static indeterminacy will be either external or it will be internal. Now we need to find out whether this is external or internal. So we first check the external indeterminacy. So if we check it, this is R minus 3. R is the number of support reactions, which are 3 in this case. So 3 minus 3, this gives you 0. This gives you 0. It means that this given truss structure is externally determinate, which means that there is no extra support reaction which cannot be solved using the equilibrium equations. Okay, all these reactions, 1 here, 2 here, they can be solved using the equilibrium equations. So this means that if there is no external indeterminacy, so this one will now go to the internal. It means that there is one extra member force which cannot be solved using the available equilibrium equation. So it means that in the next step, we have to release a member force and write our redundant action corresponding to that member force. We don't now need to release the support reaction. Why? Because the external indeterminacy is equal to 0. Okay, this structure is externally determinate, so we will not release any support reaction. We will only release a member force, because we have one extra unknown member force. Okay, so I choose to release the member force in this member AD. Okay, you can choose any other. I have chosen this member force in member AD, and I have shown the released force by a redundant action AR, which I have shown in this direction. Okay. Now, I don't write here AR1 here because I know that there is only one redundant action. So I don't need to write AR1, AR2 here. I just need to put AR only, because I know that there is only one redundant action. But what is the value of this redundant action? This is unknown. This is unknown. And we will be looking for this value. We will be solving for this value, actually. Okay, we will be using this flexibility method for finding out this AR value. Now, what is the DRS value in this case? The DRS value is the support settlement, or support translation, or support rotation corresponding to the chosen redundant action. So we have chosen this redundant action, and there is no settlement rotation here. So it means that the DRS value will be 0. DRS value will be 0. Okay. So this is our released structure. We also call this as the primary structure and BDS. Okay, basic determinant structure. And as you know now that in the step number 3, we have now to analyze this BDS for different conditions. First, we will solve this BDS for external load, for the actual external load. Okay. So this is the given BDS. These are the loads acting. Now, this VB is unknown. This force at B. This VA is unknown. This is this force at A, this vertical force. And this HA is unknown at this A. Horizontal action, okay, at A. So we find out these values, the values of these forces, by using these 3 equilibrium equations: summation of moment, summation of this vertical forces, and summation of these horizontal forces. So first, if we apply a moment, summation of all moments about A is this joint. So if we take moment of all the forces about this joint A, so let's see which forces are causing moments. The sign convention will be that the clockwise moments will be taken as positive and anti-clockwise moments will be taken as negative. So let's see. This is the externally applied load at this joint C, and this load is actually causing moment about A in this clockwise direction. Okay, so the moment magnitude will be equal to this force times the moment arm. The moment arm is equal to this 15 feet, whereas the force magnitude is 10 kg. So we will be taking it as positive because it's clockwise. So we have taken it equal to 10 into 15. Okay, 15 is the moment arm, 10 is the force magnitude. Okay. Now let's see if this 20 kips load is causing any moment about A. So is it causing any moment? We have the force magnitude, but we don't have any moment arm for this force. Okay. So if the moment arm is 0, it means that this force will not cause any moment about this joint A. So we will not consider this. Okay, this is 0. The moment due to this is 0. Okay, now let's see what else we have. We have now this unknown support reaction. We have this unknown support reaction VB, and we have assumed it to be acting upward. We have assumed it to be acting upward. So by assuming it acting upward, now let's see what effect it is causing about this joint A. So the force magnitude is unknown. The force magnitude is unknown at this point. And the moment arm for this unknown force is 20 feet. So we denote this unknown force by VB, and the moment arm for this is 20 feet, and it is causing a moment in the anti-clockwise sense. Okay, so we will be writing a negative sign with this, and the moment will be equal to the unknown force VB times 20, which is the moment arm. So let's see if there is any other force causing moment about this A. So if we are left now with this VA, which is the unknown force, with this HA, which is the unknown force. So if we see them, we see this, that there is 0 moment arm for VA, as well as there is 0 moment arm for this HA. So it means that they cannot cause any moment about A. Okay, so we will not consider their effect. So we see that if there is any other force left, so no, there is no other force left. So now we solve this equation and we take this equal to 0. So we solve this equation now for this unknown force VB. So we come out with the VB value of 7.5 kips. And this 7.5 kips is actually this unknown force. Now this is known, and its magnitude is 7.5 kips, and it is acting exactly in our assumed direction, which is upward. Okay, there is no negative sign with this. It means it is exactly acting in our assumed direction, which is upward. Now, in the same way, we can apply another equilibrium equation, which is the summation of Fy. So we sum all the vertically acting forces, and we take their summation equals to 0. So let's see how many vertically acting forces we have. We have this 20 kip. Okay, we have this 20 kip, and this is acting downward. So the sign convention is that upward should be taken as positive, and downward vertical force should be taken as negative. Okay, so this is 20, so we'll be taking it as negative. What else we have? We have this VB, which is now known to us. This is acting upwards, so we'll be taking it as positive. Okay, so the equation will be looking like minus 20 plus 7.5. And what else we have? We have this VA, which is unknown at this point. Okay, this VA is unknown at this point. So we represent this by VA, and we assume it to be acting upward. So we will be taking it as positive. So minus 20 plus 7.5 plus VA equals to 0. So if we solve it for VA, we then find out that the value is 12.5 kips. Okay, so now VA is also known to us, and the value is 12.5 kips. Similarly, we now apply the third equilibrium equation, which is the summation of horizontal forces equals to 0. So we will first check how many horizontal forces we have. So we see that there is this one horizontal force acting at C, and there is this horizontal reaction at A, but the value of this reaction is unknown, and there is no other horizontal forces. Okay, so what we do now, we simply take the summation of these horizontal forces, which are externally applied. So we take rightward as positive and leftward as negative. So this becomes minus 10 kips, and this is the assumed direction. So minus 10 kips plus HA equals to 0, and we come up with a value of this unknown horizontal reaction at A to be equal to 10 kips. Okay, so by using the three equilibrium equations, we found these values of the unknown reactions. Okay, so now they are known. Now in the next step, we need to find out the member forces now. Okay, due to externally applied load and these reactions, we now need to find out the member forces. So we will be needing in the later calculations, as we'll be doing by using the method of joints. You already have solved method of joints in your structural analysis 1 course, so I think that will not be that much issue. But we will be, but you know now that we frequently use these functions, sine theta and cos theta. So let's find their values here. So how can we find the value if this is our theta? This is our theta. So for this theta, this is the base, and this is the perpendicular. So if we take 10, we want to find out this theta. So in order to find this, we should apply a function of this theta, which is in term of the known values. So the known values, we have this 15 feet and 20 feet. We don't want to involve this or this at this stage, because we then have to do extra calculations for that. So if I take tangent theta, this will be equal to perpendicular over base. Perpendicular is this 15 feet and base is 20 feet. So tangent theta will be equal to 15 by 20. Now, if I want to find theta, I'll take tangent inverse. So that theta will be equal to tangent inverse of 15 by 20, and it is equal to 36.86 degrees. Okay. So if we take sine of this, it is equal to 0.6. And if we take cos of this, it is equal to 0.8. So it is good that you do it in this step, so that later if you see sine theta, sine 36.86, so you directly put 0.6 there. It will save some time. Okay. Okay. So now let's apply the method of joints here. And we are applying this method of joints for finding out the unknown member forces due to the externally applied load. Okay, so we first start with this joint A, joint here. So now if we take this joint A, we can see that on this joint A there is a member force applied to this AC, member AC, and there is also a member force applied through this member AB. This member we have released, so there is no force, member force coming from this one. So we have one member force if AC, we have one member force if AB. These are the member forces, and external reactions are this 10 kips, this one at this joint A, and this vertical reaction which is 12.5 kips, this one. Now if you apply the equilibrium equation at this joint, you can find out very easily the values of this unknown member force in member AC and this member force in member AB. So if we apply summation of Fy equals to 0, how many vertically applied forces we have on this joint? We have this 12.5 kip acting upward. We have this, we have assumed that if AC is also acting upward. So we will take both as positive. So if AC plus 12.5 kip, this is equal to 0. So if we solve this, we get the value of if AC to be minus 12.5 kip. Minus 12.5 kip. And this minus will mean that there is tension in this member AC. There is tension in this member AC. Okay, now we want to find the member force in this AB. For this, we apply the summation of Fx equal to 0, summation of all the horizontal forces equals to 0. So how many horizontal forces we have? We have this 10 kips and we have this FAB. We have assumed this FAB to be acting rightward, while the 10 kip is acting actually leftward. So rightward is positive, leftward is negative. So FAB minus 10 kip equals to 0. This gives you FAB equals to 10 kips. So this is the member force in AB. And this positive sign shows that this is compression in this member. There is compression in this member AB. So these are the members which we have solved from this this joint A. Now we want to solve the other members also, for which we need to take other joints. So now we take the joint B. Now for this joint B, we know that this member force is acting. Also, this member force is acting in this inclined member, and also this member force is acting, this vertical member, BD. But how many known member forces we have? We have this member force of known magnitude, and the magnitude which we have solved on the previous slide. Okay, so we will be now taking the value from that slide, okay, and use it here. So, and that value was 10 kips. Okay, so we have assumed this FBC to be acting in this direction, and we have assumed FBD to be acting in this direction, whereas this vertically applied reaction here, this is acting upward. Okay, so now again, if we take summation of Fx, so how many forces here which are acting along the x-axis? So if you see here, we have this 10 kip which is acting in the this negative, not positive, so this will be minus 10. And if you see, this is inclined force. This force can be resolved into a vertical component and into a horizontal component. So the horizontal component of this inclined load is equal to FBC times the cos of theta. Okay, so it means that horizontally we have this 10 kips load or force, and we also have FBC times cos of theta. Theta is 36.86. So it means that this force FBC is, if it is acting in this direction, so its horizontal component will be acting in the negative direction. It will be acting in the negative direction. So this will become minus 10 kips. Okay, minus 10 kips minus FBC times cos of 36.86 equals to 0. So by solving it, we comes up with this FBC to be equal to minus 12.5 kips. And this minus shows that there is tension in this member BC. I hope this is clear. Okay, I hope this is clear. If you have any question, you can comment or you can say. We can solve that. Okay, you can also now see it in the next one. Okay, now let's apply the other equation. We now know the value of this member force FBC, which is tension, and it is 12.5 kips. Now we are left with this FBD, and if you apply the summation of vertical forces equals to 0, so we have this FBD with the assumed upward direction, which is positive. So FBD plus 7.5 kips. And now we have one vertical component of this FBC. Okay, so that of course will be acting in upward also, and it will be equal to FBC times sine of 36.86. Okay, acting upward. So now our total sum is FBD plus FBC sine of theta plus 7.5 equals to 0. Okay, so if we leave this FBD on one side of the equation and shift the others to the other side, so now they have negative sign with them, and if we solve this, we come up with the FBD value equals to 0 kips. Okay, so it means that there is 0 kip member force in this member. Okay, so now we have solved from this joint, using this joint, equilibrium on this joint, we have solved this member force. Also, we have solved this member force. So the only member force we are left with is now this CD. So for this, you can take this joint C or you can take this joint D. So I take this joint D. This will make the calculations simple. so simpler in fact. So if we apply the same at joint D, now we know that at joint D, one member force is coming from this member, but this is 0. And one member force is coming from this member, which we have to find. This is unknown. And there is no applied external or member force on this joint. Okay, so this is FDC. We assume it to be acting in this direction, negative. And there is no other force acting. Okay, this is also 0. So it means that FDC is equal to 0 kips. So now we write all these values with the members. So we now know that this is 12.5 kip and it was in tension. So we shown this now by tension. This was 10 kip compression. This was 12.5 kip tension. This is and this member, it was 0 and it was 0. So now from this slide, we have to pick the values of capital P. Okay. And then we have to use them in the later calculations. Now let's move to the, I think this is clear. This was the method of joints we have applied. So now in the next step, we have to analyze the BDS, and this analysis should be for a unit load, and that unit load should be at the chosen redundant location. So this was our chosen redundant location. So we apply a unit load now of 1 kip, and now we solve all these member forces. So how it can be solved now? Using, again, taking the joints and solving. So we take this joint D, on which now this one force is acting, one kip force is acting, and this FDC is acting, and also FBD is acting. Okay, so now we have to find out these values of this CD and this FBD. So if we apply summation of Fx, we find out the value of FDC to be equal to negative 0.8 kips. And if we apply summation of Fy on this joint, so we can find out the values of the value of FBD to be equal to negative 0.6 kips. In the same way, we apply the equilibrium equation now at joint C, and at joint C we now see that this member force is acting, this member force is acting, this CB, also this member force is acting, CA. And now we are not taking any external load, right? We are not taking any external. We are only taking this 1 kip load applied at redundant location 1. So if we apply summation of Fx equal to 0, this gives us the value of member force in member CB to be equal to 1 kip. And if we apply summation of Fy equals to 0, this gives us a value of FCA, which is the member force in the member CA, equals to negative 6 kips. So this is now tension, and this is compression. Okay, similarly, we can find out the values of FAB equals to negative 0.8 by applying the summation of Fx at this joint B here. And we also find out this VB equals to 0 kips, and this VB is the vertical reaction at this joint. Okay, this comes out to be 0 kips if we apply summation of Fy. Okay, so we finally come up with these values. These are the member forces which we just calculated by using the method of joints. This is now compression, sorry, this is now tension. This is compression. This is tension. This is also tension. This is also tension. Okay, and all these member forces are due to this 1 kip applied load. Okay, so the member forces, now we will be using them in the later calculations as U values. Okay, so now let's develop our table. All these member forces, we now need to write them in a table. So these are all the members: A, B, B, C, C, D, okay, A, D, A, C, and B, D, and these are the values corresponding to each member. Okay, so this is the length of AB. This is the capital P value, the member force due to external load for member AB, and the unit for the member force due to unit redundant action. Okay, this was in the member AB. This is the value. So similarly for the other members, these are the values. Okay, we have summarized them in the form of a table. Now in the Step number 5. Now in the next step, now we are going to calculate the values of DRL matrix. Now, as we know that the DRL value, it corresponds to the displacements, and these displacements are due to the external loads applied on the structure. Okay, so the displacements can be determined by this equation, and this equations in this equation, if you see, we have this capital P. Now we can pick all these values of this capital P and this capital U and this capital L. We have already discussed that this capital P is the member forces, and those member forces are coming from the externally applied load. When you apply external load on the determinate truss and then you analyze it, so you get member forces in all the members, and you call those member forces as capital P. So the values of the capital P for the first member AB, it can be found in this table, and here it is in this column, right? This column. So for the first member, AB, the capital P value is 10, and you can see it is written here 10. Now the capital U value is coming from this column for this element AB, and it is equal to negative 0.8. So we can see it is negative 0.8. Okay, and the L is the length of the member AB, which is 20 feet. We can see in this table. So now we picked values for the member AB, right? Now we need to pick the values for the member BC. So for member BC now, we pick this 25 value from the length, this length. This negative 12.5 is coming from this capital P value for member BC. And this 1 value is coming from this column, which is U1 value corresponding to member BC. Okay, so you simply need to multiply the capital P value, the capital U value, the capital L value for each member, and then you need to sum them, right? You need to sum them. So as we can see for the member CD, there is the P is equal to 0. So this makes the whole product equals to 0. Okay. Also, member AD, P is 0. So the whole product will become 0. If you look at the member AC, so the length is 15. Okay. In this member AC, this is the length, which is 15. And negative 12.5 corresponds to the capital P value. And what is capital P value? P value is actually the member force when external load was applied on the basic determinate truss. Okay, so this negative 0.6, this is this value, this U value, which is coming from the analysis of BDS when subjected to unit load corresponding to redundant location number 1. Okay, so similarly you apply this term for this BD member, and in this we can see that the capital P value is 0, so the whole product becomes 0. Now if you solve this, you get the value of your DRL to be equal to negative 360 divided by EA. Okay, so what is this displacement corresponding to redundant location due to the externally applied load? Okay, and we have only one DRL value. Why? Because we have only one redundant action in this problem. Okay, in this problem we have only one redundant action. That's why there will be only one value in the DRL matrix. I hope this is clear to all of you. So now we move to the next step, in which we will now be calculating the flexibility coefficient matrix. So again, as there is only one redundant action, so the in the flexibility matrix there will be only one element. Okay, and that element will be F11, the displacement at 1 due to unit load at 1. Okay, so the flexibility coefficient correspond to the displacements at redundant locations when a unit load is applied at any one of the redundant locations. Okay, so this can be determined by using this equation. Now in this equation there is no capital P. We only will use the capital U, and we know that what is capital U. Capital U is the member forces, member axial forces, which are coming from the analysis of the truss when subjected to a unit load corresponding to redundant location. So now both times this U will be multiplied and then with the length. So now in this step, this P column, this capital P value column, this will not be used. We'll only be using this length column, okay, this length column, and this capital U column, okay. So if we do it for the member AB, for this member AB, we can see that the length is 20 feet. So the length is 20 feet here. And now we need to take the value of U 2 times. So this is negative 0.8. This is negative 0.8. Okay, this is negative 0.8. So we take it as negative 0.8 here. And again, we take the same negative 0.8. Okay. So this is for the member number 1, which is AB. Now we take the same for member number 2, which is BC here. So 25 feet is the length, and this 1 is the U value, which we take 2 times here, right? So similarly, we repeat all this for the member number 3, for member number 4, 5, and 6, okay? And then we sum them, so we get the value of F11 to be 86.40 divided by EA, okay? So the flexibility coefficient matrix comes out to be equal to 86.40 divided by EA. So once we get this, now in the next step, we now need to simply plug in those matrices in this equation to find out the value of the unknown redundant action, okay? If this is the flexibility matrix F, we already determined, okay? Only one value it has. We know what is DRS. DRS is the support, settlement, rotation, or translation, okay? And what is DRL? So DRL is the it is the displacement corresponding to redundant location due to external load, okay? So now we put the values in this in this equation. These are the matrices we already determined in the previous steps. So we come up with the value of AR to be equal to 4.11. So this is now the unknown redundant action. Now it becomes known to us. So if we want to find out the member forces, so we can find them by this equation. And in this equation, again, the AML is corresponding to the member forces when external load was applied, okay? So if we choose our AM1 to be the member force in this member, AM2 to be the member force in this member, okay, in this member. Similarly, AM3, and then the AM4, AM5, AM6. So now we need to find these member forces. So corresponding to each AM1, 2, from this here, we have to find out the values from the already analyzed structure in the step number 3. So now this is our chosen AML1, okay? So the value corresponding to this in this analyzed structure is 10 kips, so we take this value to be 10 kips. Similarly, our chosen AML2 is this one. So this is 12.5 and it is in tension. So this will be minus 12.5. And similarly for ML3, ML and ML4 corresponding, the values are 0 here. This and this. And AML5, which is this one. So we see that this is minus 12.5. And similarly the AML6, which is this member, so the force is 0 here, so this will also be 0. In the same way, we need to find out the values of the AMR matrix, which will have only one column now, because we have only one redundant action and we have to apply a unit load and then we have to find the member forces. So this we solved in the step number 3, Okay, this is the AML matrix, this is the AMR matrix, this is the AR. So we come up with this final values of the member forces. Okay, this is the final outcome of the member forces: 6.71 compression in the first member, and this negative 8.39, which is the member number 2 tension. Similarly, all these are the member forces in the remaining members. So now this is our final and completely analyzed structure. We know the support reactions we already calculated in the previous step, and now we also come up with the member forces. Okay, so now this was all about example problem number 1. I hope this was clear to all of you. Now let's do another problem on this. Let's quickly do this problem. Now this is the same structure as we analyzed in problem number 1, but now we have only one extra support. Now what this extra support will be causing? Now let's see its effect on the total static indeterminacy. If you check out the total degrees, in the previous case it was 1 degree. So now this 1 more degree is coming from this support, this extra support. Okay, so now if you find out the external static indeterminacy, this comes out to be 4 minus 3 equals to 1 degree, because now we have one extra support reaction. So now the total support reaction becomes 4, and if subtracting the number of equations, so you get 1. And the internal static indeterminacy will be subtracting from the total this external indeterminacy, so you come up with 1 internal. So it means that we have 1 external static indeterminacy, which means we have 1 extra support now, and we see that this is now the extra support. So we have 1 extra unknown support reaction, and also we have 1 extra support, this member force. So let's quickly do this, because we already know all these steps from the previous problem. So we just need that what changes now we will be doing. So now our AR will be now 2, because we have 1 member force and we have 1 extra support reaction. So the support reaction, we choose this to be, we release this and we choose this to be our AR1, and this we choose to be our AR2. This we choose to be our AR2. Okay, so these values are unknown, AR1 and AR2. Okay, the DRS1 value, the support settlement corresponding to redundant location 1, there is no support settlement or rotation or translation. This value is 0. Also, there is no settlement or translation or rotation corresponding to this redundant location. So this value is also 0. Okay. So now the next steps are exactly the same as we did in the problem number 1. We will analyze the whole structure for this external load. By whole structure, I mean the BDS, the basic determinant structure, which we obtained by releasing this support, this extra support we have. Okay. So by applying these equations as we did in the previous problem in detail. So here, I'm not going into detail, as we already did there in problem number 1 in this lecture. So you come up with the values of VB, VA, and HA as given here from these equations. And now you need to find out the member forces. So we will be exactly using the same procedure. We'll take a joint A and solve for these values. We'll take joint B and solve for these values. Then we'll take joint D to solve these values. Okay. So this is the now the solved BDS, the external load, for the external load of this 20 kip and 10 kip and these reactions. Now we need to, in the step 2, we need now to apply a unit load corresponding to a redundant location, 1 at a time. So we apply at the redundant location number 1, this 1 kip load. And now we analyze the whole structure due to this 1 kip load. So again, in the same way, you apply at joint A, at joint B, and at joint D. and those equilibrium equations, and then you come up with these member forces. Okay, so from this slide you are going to take the values of this capital U. The same way, now you have to take one redundant action corresponding to the redundant location number 2, one unit load corresponding to the redundant location number 2. So when you do this, you need now to apply the method of joints exactly in the same way as we already did. So we come up with this solved structures. From this, now we will be taking the U2 values. Okay, there is nothing changed now. We have only one extra redundant action in this problem number 2. So now we will have one extra column. This is the U1 column, this is the U2 column. U1 column is coming from when the unit load was applied at redundant location number 1, and these are the member forces. Similarly, the U2 values are the member forces in all members when a unit load was applied at redundant location number 2. Okay, so now we need to find out the DRL1 value and DRL2 value. The DRL1 value, now we will be taking the values from the U1 column here and also from the P column and this. Okay, so if you do this, you come up with the DRL1 value equal to this one, and similarly you can find out your DRL2 value. You can pick these values from this table. So in this way you get this DRL matrix. So the change from the previous problem is that we have now one more displacement. We now need to find out the flexibility coefficient matrix, which will now consist of 2 cross 2 matrix. So this is the displacement 8 redundant location 1 due to the load applied at location 1, and that load is a unit load. So when you solve this, you find out the flexibility matrix to be equal to this one. Okay, so now you plug in all these values. You plug in all these values in the in this equation. Flexibility matrix we know, the DRS we know, the DRL we know. So if you plug in all those matrices, you come up with your AR1 value to be equal to minus 5.14 and AR2 to be 0. It means the member force is 0, AR2 is 0, and AR1, which was the support reaction, it is minus 5.14. We need now to reverse the direction. Okay, our assumed direction needs to be now reversed in the case of this one. So now this is our structure determinate. Our assumed direction of this AR1 was like this. So we have now reversed this, and we have this AR2 equals to 0. So now this is 0. Okay, now you can find out the member forces exactly in the same way as we did in the problem number 1. AML, AMR we need to calculate. AML will be coming from when we solve the truss for externally applied load, and which truss? The basically determinate truss, which was basically determinate. Okay, so these are the AML values, and then you now in this case our AMR matrix will be consisting of 2 columns. The first column will correspond to the member forces which are coming from when unit load was applied corresponding to redundant location number 1. Okay, and the second column will be coming from the truss structure which we solved for a unit load corresponding to redundant location number 2. Okay, so when we do this, we come up with AMR matrix, and now if we plug in all these values in our equation, so we come up with these member forces. Okay, these member forces, and this is our final completely analyzed structure. We have all the member forces known, okay, and we have all the reactions known. So this is the method of flexibility for truss structures. Okay, I hope all are clear to you now. Do you have any question? So now you can ask. Okay, I'll answer you one by one.